Welcome back. In this video, we're going to be studying a problem involving refraction, or the bending of light as it passes from one material to another. And along the way, we're also going to be using the concept of total internal reflection. Go ahead and take a look at the problem statement. So as you read in the problem, we have a situation in which light is coming from air towards a glass surface. When it hits the surface, it's going to refract towards the normal. This always occurs when you have a lower refractive index, which is air, it's 1, it's the lowest it can be, to a higher refractive index of glass. It's always going to bend the light towards the surface normal, so it's going to bend it inward. And then when it's going to continue passing, then when it gets to the other glass surface here, it's going to totally internally reflect, which means the following. It means that when you have light going from a high index to a low index, it's going to bend away from the normal. If this angle is big enough, that refracted light will actually be parallel to the surface. And any angle bigger than that means the refracted light won't exist. So a total internal reflection means that the refracted ray will not be present, and all you're going to have is a reflected ray. This will occur when you pass from a high index material to a low index material if the angle is big enough. The angle at which it first occurs is called the critical angle. And so what we're saying here is that we're asked to find what is the minimum refractive index of the glass for which there is no refracted ray. In other words, the only thing that occurs is reflection. We're told that the angle here is 45 degrees, but that's it. So what we're going to do is apply Snell's law twice. Snell's law is what you always want to be using for refraction. And using those two equations, we can combine them to find out what n has to be. Let's first, let me just recall what Snell's law is. Snell's law says that the product of the refractive index and the sine of the angle is the same on both sides of any sort of boundary. Let's go ahead and apply it first to the point A. So at point A, we have the refractive index outside, where it's air, is just 1. So n1 is 1, and the sine of the angle is sine of theta. What you always want to make sure is that the angle in Snell's law is always measured from the surface normal. So you don't want to be using this angle here. You want to use the angle between the ray and the perpendicular direction of the surface. In this case, that's theta 1. So we have, for point A, we have 1 times sine theta 1 equals, now on the other side we have, let's just go ahead and mark out this angle here. This angle, I'll call it theta 2. And again, notice I'm drawing it from the surface normal. I'm not calling that theta 2 because that's not the angle that's used in Snell's law. We have a similar thing. So I'm going to call the refractive index of the glass just as n. So this is going to equal n times sine of theta 2. Since we have theta 1, we don't know theta 2, and we're looking for n. We're going to need one more equation. Let's go ahead and repeat this at this boundary here. And we're going to keep in mind that when you have the critical angle, which is when total internal reflection first occurs, the refracted ray is going to be parallel to the surface. Okay, so you can consider that as a refracted ray of 90 degrees to the surface normal. Right? So basically the ray is coming in like this, which is 90 degrees with respect to that surface normal. So the outgoing angle will be 90 degrees. What's the incoming angle? Let's go ahead and again draw the surface normal on this side of where the light is coming from. So we're going to need this angle right here. If you use a little bit of geometry, you'll see that this angle is theta 2 means that this angle is theta 2 right here. So this is 90 minus theta 2. That's the angle I got to use in Snell's law. So the refractive index of inside the glass is n. The angle is 90 minus theta 2. And outside the glass, again, the refracted ray at the critical angle is going to be basically coming like this. Okay. Anything bigger than that is going to have no refracted ray. So we're looking at the critical angle where this is 90 degrees. The surface normal is like this, so the angle between those two is 90 degrees. So n for air is 1, so it's just going to be sine of 90, which is 1. And that's always the key at the critical angle where total internal reflection first starts to occur, is that you're going to have sine of 90 equals 1. So we have two equations here. The only unknown is theta 2 and n. We can combine them to get rid of theta 2. So what we want to first do, I think, is just get rid of this 90 minus theta 2. And you can use a trigonometric identity which says that the sine of 90 minus angle is the same thing as cosine of that angle. So we'll have n times the cosine of theta 2 equals 1. Okay. So we're basically there. We just have to combine this equation with that equation. There's a little bit of algebra. You might have to use a couple of identities. So just try that real quick and try to find out a formula for n. Let me just come back and finish it up. What we can do here is use the following formula, the trigonometric identity for sines and cosines, which is cosine squared of an angle plus sine squared of the same angle equals 1. This will allow us to trade out the cosine for a sine because we want to use sine up here. So let's go ahead and let me square this formula. So we'll have n squared cosine squared of theta 2 is 1. And we can use the fact that 1 minus sine squared equals cosine squared. So plugging this in here, we get n squared times 1 minus sine squared. That equals 1. So solving this for sine squared, we'll find that sine squared of theta 2 is, let's see, so this will be 1 over n squared. Put this over here, we'll have 1 minus 1 over n squared. Okay. And then finally I can plug that guy back into equation A. That should give us, and I'm going to square A first, so that'll give us sine squared theta 1 equals n squared sine squared theta 2. And then plugging that in here, and then sine squared of theta 1. Theta 1 is 45, so this is going to be 1 over square root of 2 squared. So you just get 1/2 equals n squared minus 1. So n equals the square root of 3/2, which is 1.22. So this is saying that you have to have a refractive index at least of 1.22 to get total internal reflection over here. If anything is bigger than that, if it's 1.3 or 1.4, you're still going to get total internal reflection, although the angles may change, of course. And that's the answer to the problem. So it's fairly straightforward. Just make sure that when you do these types of problems, you're being careful of labeling the angle between the surface normal and the ray, and then you just have to use a little bit of trigonometric gymnastics to figure it out. So that's that. Take a look at the summary, and if you have any further questions on the algebra, look at the write-up that's attached to this video. See you next time.